Hello, my name is Leke Akinola. Today I'll be talking about my work towards online training of spiking neural network using domain wall magnetic junction synapses. I have done this work in collaboration with other people from UT Austin, UT Dallas, and Standard National Labs. First, I'll talk about the basic concept, then I'll move on to the work we do, and then I'll give the summary slide. What do I mean by spiking neural network? Spiking neural network is a third generation neural network, artificial neural network that captures the functionality of the brain more accurately. This is an improvement over the second generation artificial neural network and the fourth generation artificial neural network, in that in the first generation ANN, which is the maculopit neuron, signals are in forms of zeros and one binary states, whereas in the second generation ANN, signals in forms of real values between zeros and ones. Whereas in the spiking neural network, we have signals encoded in forms of spike train, and this can follow frequency encoding or time encoding. But the major thing to highlight here is that the spiking neural network helps to capture the functionality of the brain more accurately. Now, the spiking neural network is also the fundamental basis of neuromorphic computing, which mimics the brain. And the two fundamental cells that we need to understand how it works is the neuron and the synapse, which make up the brain. The neuron helps with acquiring signals from other neurons or from the outside world, and these signals are added together in form of a transfer function or summation function, and then goes through a transformation function that converts the signals into an action potential that goes down the axon down to the next neuron. Now, the gap between neurons is called synapse, and this synapse is fundamental in the weight, in defining the weight between neurons, and it needs to be this weight needs to be dynamically adjusted to reflect how each neuron connects together. So we need some basic component that will help us to be able to dynamically adjust the weights between two fundamental neuron components in a way that it's dynamic, predictable, and can be done in situ. One other thing that is needed to highlight here is the concept of spike time independent plasticity, which is a function of the correlation between the timing of the signals that come into the synapse from the presynaptic neuron and postsynaptic neuron, and how much the weight in the synapse is adjusted. This shows that when the presynaptic neuron signal comes before the postsynaptic neuron signal into the synapse, then there is higher weight adjustment in the positive direction, and when the presynaptic neuron signal comes after the postsynaptic neuron signal, then there is a depression or a decrease in the weighting. Now, this is very analogous to a time-dependent resistor or a current-dependent resistor, in that the strength of the conductance of the resistor is highly dependent on the timing of arrival of signals on both ends of the resistor. When the difference in timing is low, then there is a strengthening of the conductance of the resistance. But when the timing is higher, the difference in timing is higher, then there is an increase in the resistance of the resistor. And one component that helps us to be able to capture this more accurately is the magnetic junction, or the domain magnetic junction. Here we show the domain magnetic junction used as a synapse, and below here we show how it's used as a neuron. One thing that's fundamentally different between the two of them is the length of the ferromagnet on top of the tunnel junction. In the synapse, the length of the ferromagnet is longer, whereas for a neuron, the ferromagnet on top of the domain wall, on top of the tunnel junction, is shorter and is towards the rear end there. And this location of the ferromagnet helps better in thresholding, such that when the domain wall moves all the way to this point, then there's a sudden increase in current that corresponds to spikes. Now, we should be able to wire together the synapses and the neuron in a way that helps us to be able to do some machine learning. Let us look a little more deeply into how the synapse is designed. Now, the synapse is designed by putting a 3-terminal magnetic junction or a domain wall magnetic tunnel junction in between two RC circuits, and such that when the presynaptic signal comes in before the postsynaptic signal, the current moves in one direction, and when the postsynaptic signal comes before the presynaptic signal, the current moves in the opposite direction. And this current is proportional to the delay between the presynaptic signal and the postsynaptic signal. We decided to go ahead to do some SPICE simulation to observe how much current goes through and what direction of current, to verify this. And this shows that when the presynaptic signal comes in before the postsynaptic signal, then we have a positive going current. When the postsynaptic signal comes in before the presynaptic signal, we have a negative going current. We decided to plot the different amplitude of the current with the delay, and we realized that it corresponds to what Bai and Ho did in their work, that the delay is inversely proportional to the current that flows through the device. And one other thing that we observed is to see how the domain wall moves in response to if the presynaptic signal comes in first or the postsynaptic signal comes in first. Then we realize that indeed the domain wall moves in one direction when the postsynaptic signal comes in before the presynaptic signal, and then when the presynaptic signal comes in before the postsynaptic signal, the domain wall moves in the other direction. And one other thing we also try to verify using SPICE is seeing how much correlation there is between the delay and the movement of the domain wall. We realize here that when there is a 1 nanosecond delay, the domain wall actually moves much more significantly across the track, and when the delay is larger, the movement of the domain wall actually is limited or is slower. And this shows to us that the domain wall, the rate of change of movement of the domain wall is proportional to is inversely proportional to the time delay between the pre and the post synaptic signal. We also decided to check this behavior using micromagnetic simulation using these parameters. We see indeed that when the pulse is moving in one direction, or the pulses are positive, the domain will move in one direction, and when the pulses are negative, it moves in another direction in a predictable manner. The notches are actually put there such that the domain wall can be moved in a predictable and controllable manner, and in a way that it's very repeatable. The TMR ratio here helps us to be able to calculate the conductance weights that correspond to each of these domain wall positions. I realize that the conductance weight varies based on the voltage polarity and based on the position of the domain wall itself. Lastly, we decided to check the crossbar array and see, put the synapses in the crossbar array and see whether our hypothesis is able to hold up. And realize that the synapses actually behave the way we want it to behave when put in a 2x2 crossbar array, and this gives a lot of light for scaling it up to a 10x10 or 100x100 crossbar array format for real machine learning task. Here we see that for the synapse 2, where the delay between the presynaptic signal and the postsynaptic signal is shorter, the domain wall actually moves much more rapidly across this path, whereas for synapse 3 and for synapse 4, where the delay between the presynaptic signal and the postsynaptic signal is higher, the domain wall actually moves much less gradually, or in a much more delayed fashion. And so one other thing that is important to note here is how the synapse 3 and synapse 1 actually has a head start in its movement compared to synapse 2 and 4, and this is because for synapse 1 and 3, the presynaptic neuron signal actually comes in earlier compared to synapse 3 and 4, where the signals actually come in a lot more later. 2 and 4, where the signals come in much more later. And in conclusion, we're able to see that the more we can capture the basic functionality of synapse, the synapse models spike time independent plasticity, the behavior of the synapse is consistent with a 2x2 crossbar array, and this shows a lot of promise for real-time machine learning application. Thanks to our collaborations, and thank you.